what I intend to do in this seminar is essentially go through two other examples. Last time we did row clone. Hopefully it was interesting. I mean, if you have any questions on row clone, maybe what we can do is we can take it at the end of meeting 3A, and then we can decide if you want to have meeting 3B, depending on how much time we have, of course. So keep in mind any questions you may have on row clone, and of course develop some questions on memory channel partitioning also. So I intend to present this paper. Okay, I see my slides moving with some delay, but at least they're moving. And this paper is a paper, again, it's my own paper, so it helps to give you a historical perspective also, if it's your own paper. I don't think you'll have the luxury to do that in this course, but it won't be your papers basically. But it's always good to present your own paper after, let's say, I think in this case, 9 years, right? To give you a different perspective that you may not get anywhere else. So we're going to look at this paper, which was published in Micro. It's titled Reducing Memory Interference in Multi-Core Systems via Application-Aware Memory Channel Partitioning. And clearly, I like this paper. And I'll maybe give you a historical perspective at the end also. So again, I'm going to follow the same guidelines that we had given you on how to present in the seminar. Again, I see a delay, unfortunately, in my other screen, delay in terms of this, when the slides are displayed. I'll try not to go too fast in the presentation. Okay, so as we mentioned, you start with background, problem, and goal. Okay, it takes a while to get to the slide. And this paper, basically, let's go through these background. What this paper is trying to solve is, again, main memory is a bottleneck. As you can see, main memory latency is long. As a result, the core stalls for waiting for memory requests and performance regrades. Now, in modern systems, you don't have single core, you have multiple cores. And in this case, 2 cores, for example, multiple applications share the main memory. In this case, red and blue application, for example. Now, this leads to the problem of inter-application interference. Basically, both cores may generate requests to main memory, and the applications that are running on these cores may interfere at the main memory because of these requests that are interfering with each other. So this is called inter-application interference, and it degrades system performance compared to when a single application is running on any of these cores, clearly, right? Okay, so the problem is further exacerbated due to increasing number of cores. So this problem will get worse because the number of cores are expected to increase, or number of agents, number of accelerators, whatever goes to the memory controller basically to access main memory. And this memory bus is bottlenecked by bandwidth. Basically, there's limited off-chip pin bandwidth, as we have discussed last time, right, when we talked about row clone. Okay, so that's basically the problem that this paper is tackling. So what is the goal of the paper? So the goal of the paper is to mitigate this inter-application interference. So the previous approach that the paper realizes, the previous predominant approach to mitigating inter-application interference is to do application-aware memory request scheduling. Basically, the memory controller tries to sort out, prioritize these requests to mitigate the interference as much as possible. Now, this paper introduces 2 approaches. The first approach is called application-aware memory channel partitioning, as we will discuss. Basically, it partitions the application to different channels. And the second approach integrates this channel partitioning with some amount of intelligent memory request scheduling. So this is called IMPS, integrated memory partitioning and scheduling. So clearly, slides are lagging, unfortunately. I don't know what to do about this, frankly, but I will try to realize the problem and go slower. Okay. So, okay, the paper talks about some background, which is main memory, which all of you are quite familiar with, I believe, at this point, but I'll go through it. Essentially, main memory consists of multiple banks, and each bank has a row buffer in it. Each bank is a 2-dimensional structure of rows and columns, and a row buffer houses, turning off the video helps. Okay, if you think that would be better, let's try that. Somebody suggested turning off the video. Okay, maybe we'll turn on the video when actually needed. How do I turn off my video? Okay, I did stop my video. Yeah, let me know if it helps. If it doesn't help, I'll turn it on again because it's nicer to have my emotions perhaps as well. Okay, basically, whenever you're accessing a bank, each bank needs to be accessed through the row buffer. You cannot directly access the array. You first need to bring a row into the row buffer and amplify the contents of it. So each bank has a row buffer that has an activated row. Okay, so that's how the activation is done in memory. So okay, today's memory controllers take advantage of this row buffer. Basically, they use a scheduling policy called first ready, first come, first serve, where they prioritize the requests that hit in the row buffer first, because those requests are row buffer hits, and they're much faster than requests that don't hit in their row buffer and that require opening up or activating another row in the bank. And all else being equal, they prioritize older requests over others. And as other previous works have shown, this memory scheduling policy is unaware of inter-application interference. In fact, memory performance attacks paper, which all of y'all are familiar with because we've discussed it at some point, shows that this policy is unaware of inter-application interference. So this paper has a different take. Basically, a previous approach actually uses memory request scheduling to solve the problem or mitigate the problem. Application-aware memory request scheduling monitors application memory access characteristics. I'm going to give you a very brief overview of how that works. And then it ranks applications based on some memory access characteristics and prioritizes the requests at the memory controller based on that ranking. That's the key idea, basically. For example, it ranks applications based on the slowdowns they experience and prioritize the application that has been slowed down the most compared to when it's run alone. That's one way of ranking, right? We discussed this very briefly in memory performance attacks, full-time fair memory scheduling, if you looked into some of the later works. You don't have to, but that's the idea. Okay, so this is a very general approach. And the paper discusses the state-of-the-art work. This is called thread cluster memory scheduling. And if you're interested, I'd recommend looking into it. I don't think we are going to cover this paper in the seminar, but it's good to know how it works. Basically, this was published in Micro 2010, essentially 1 year before memory channel partitioning is published. This work actually looks at hardware threads, basically hardware context in the system. These are the threads that are executing on different hardware contexts, and classifies them as memory non-intensive and memory intensive, and basically prioritize them separately. It basically forms two different clusters in the memory control, non-intensive and intensive. And what it does is it prioritizes the non-intensive applications or intensive applications, because it realizes that if these applications are prioritized, because they create so few memory requests that if they're prioritized over these intensive applications, they're not going to make the performance of this intensive cluster suffer. As a result, it will not cause fairness problems, but this will lead to a huge performance improvement, because if these applications that are not very intensive are prioritized, their memory requests are done quickly because they don't get delayed behind these intensive applications that generate a lot of requests. As a result, the cores of these applications are kept busy much better. So that's a beautiful idea, I think. And it was the idea in this paper. And then within each of these clusters, it employs sophisticated prioritization mechanisms. For example, here, the higher priority is given to applications that are less intensive, that are generating fewer misses per cycle, let's say, or fewer misses per instruction. Here, it's more round robin based, basically, because this work realizes that intensive applications, if one of them is prioritized over another one for too long of a time, it could cause fairness issues, it could cause performance issues. It basically round robins time slots across these different applications. So there's more detail clearly in this paper. I'm not going to go into detail, but you can see that this is a sophisticated mechanism to get performance and fairness out of the system. And this was shown to be the best memory scheduler in terms of both performance and fairness compared to all other memory schedulers, but its complexity is relatively high because you need to do all of this stuff in the hardware. I need to do it periodically because applications may change characteristics over time, as you can imagine, right? So that's the idea, that's the baseline that this paper considers. So clearly this has advantages. Application-aware memory scheduling has advantages because it reduces interference between applications by reordering requests. It improves system performance as well as fairness, as shown. In this paper, the target is not fairness, the target is performance, but we talk about fairness briefly in the paper. I'm not going to go into details. But memory request scheduling actually has disadvantages also. It requires modifications to memory scheduling logic for both ranking and prioritization, and these may not be very simple modifications. And it also cannot completely eliminate interference by request reordering. Basically, it has to work with the request that already exists. It may not, if it cannot throttle, for example, the requests. It needs to work with the requests that are in the request buffer. And if there are too many requests to begin with, maybe reordering is not good enough to eliminate interference. Basically, reordering never eliminates interference. Reordering actually just reorders, reprioritizes, but it cannot get rid of the interference, right? So this paper wants to get rid of the interference. And to be able to do that, it develops this first approach called application-aware memory channel partitioning. So the observation is that existing systems have multiple channels to memory. So this is one example, red application, memory application, and there are two different memory controllers controlling two different channels. So this provides a new degree of freedom. Now you can map data across multiple channels to isolate different applications potentially. Right? So let's take a look at how mapping is done in current systems before this paper was published. Basically, the red applications pages go to different memory controllers, and blue applications pages also go to different memory controllers. As a result, applications interfere with each other in both memory controllers, right? Essentially, this is a mapping that's oblivious of applications to memory channels, right? It's not really considering interference of applications across different memory channels to do the mapping. This causes clearly interference between different applications requests, but maybe we can do better, basically. That's the paper. The paper says we can do better. We can actually partition channels between applications. So in this cooked up example, where you have two applications and two channels, you can actually completely isolate applications to different channels, as you can see. Of course, you run into memory capacity problems, which are discussed in the paper, which we will also briefly mention. But you can minimize the harmful interference between the applications because now they're isolated to different channels. So this is more powerful than request scheduling in the sense that it can eliminate interference between different applications requests by mapping them to different channels. And it can basically improve performance. But of course, there are issues. You may have more applications than channels, clearly. How do you do? And you don't want to run into memory capacity issues over here in each application. How do you handle that? So flexibility would be the answer to those questions. You will be flexible. You don't do it perfectly. You don't constrain an application to a memory channel unreasonably. If it needs more memory capacity, then you actually allocate from some other channels, giving up some of the interference elimination, but also not giving up on performance. That's the idea. Okay, so let me give you an overview of this memory channel partitioning algorithm and the idea. I guess slides are going reasonably well. They're still slow, so I'm going to turn on my video actually so that it becomes a bit more interactive, hopefully, because I see still a lag. If it becomes worse, let me know or shout out. I will stop my video. So basically, we would like to eliminate harmful interference between applications. The basic idea is to map the data of badly interfering applications to different channels. And we're going to make use of two key principles. One is, these are key principles developed by this work, but it was actually proposed by earlier work. Basically, it's applied to memory channel partitioning in this work. We want to separate low and high memory intensity applications such that a high memory intensity application doesn't interfere with a non-intensive application in the same channel, exploiting an insight that was in prior work, as you can see. And we want to separate low and high robot for locality applications such that a high robot for locality application doesn't destroy the performance of a low robot for locality application because we're using first ready, first come, first serve memory scheduling. Okay, let me give you some insight into why these work. So the first one, we want to separate by memory intensity. And high memory intensity applications interfere with low memory intensity applications in shared memory channels. Okay, so basically, we want to separate by memory intensity. We want to separate high memory intensity applications from low memory intensity applications. So let's look at on the left side of the slide over here. We have two applications. Again, this is a cooked up example, but it's always good to look at a cooked up example to see the benefits. We're going to separate these two applications to two different channels later on, but conventional page mapping may actually map the request of these applications to the same channels, right? Just like it has happened over here. Now, this doesn't sound good for the blue application because blue application finishes its request after 4 time units, and the red application finishes its last request after 5 time units. So this is the delay. Whereas if you were able to map the blue and red application to different locations, as you can see, different channels, let's say, in this case, both applications benefit. I know it's a cook example, but these cook examples can happen in real life also. Basically, you would save a lot of cycles for blue applications request, and you would save some cycles, 1 cycle in this case, 1 time unit, let's say, for a red application's last request. So that's the idea, basically. Memory channel partitioning eliminates the interference between applications and improves, in this particular case, both of the applications' performance. So mapping data of low and high memory intensity applications to different channels makes sense, basically. So the second insight is separating applications by row buffer locality. In this case, even if the intensity of the applications are the same, high row buffer locality applications may interfere with low row buffer locality applications in the shared memory channels. And the low row buffer locality application actually loses performance. So let's take a look at this example. This is the request buffer state. Again, blue and red applications. Red application has high row buffer locality, as you can see. Blue application has row buffer locality. And you can see that basically, this is what happens. And these are the row numbers where the requests are going. So row 0 gets 2 requests in this case. You can see that with conventional page mapping, the red application finishes after 2 time units, but the blue application gets delayed for 4 time units. Oh, 6 time units, sorry. If we actually map these applications to different channels, what happens is one application benefits a lot. So this one, for example, the blue application gains 2 time units, whereas the red application doesn't get affected. So it still gets its row buffer hit first policy worked well, right, as you can see. But still, this is pretty good because you're gaining overall system performance, right? Okay, so those are the 2 key insights that this work will be based on. Of course, keep in mind, whenever you're reviewing papers, keep in mind the downsides. Now, if you partition these 2 things to separate channels, there's less bandwidth available to this application overall and to this application overall, and less memory capacity available to this application. So we're not going to be very inflexible about this. We're going to be flexible. So we're going to actually take into account the memory bandwidth, and we're going to consider the memory capacity issues, as I will show you next. But the second key insight is map data of low and high row buffer locality applications to different channels. So let's go into mechanism in some detail now. So memory channel partitioning mechanism consists of 5 different steps. The first step is to profile the applications, and then we classify applications into groups, and I will talk about the groups. And then we partition channels between application groups, and then we assign a preferred channel to each application. And then, oh, wait a second. Okay, we allocate application pages to the preferred channel. So of which, the first one requires hardware, but none of the other 4 ones require hardware. As a result, the paper proposes to implement them in the system software. So this is, in my opinion, a nice hardware-software cooperative solution to the problem. So let's take a look at why this requires hardware. The first one requires profiling of applications because it requires fast profiling. Hardware counters need to collect application memory access characteristics. And these are the 2 characteristics based on the 2 key insights that we discussed. You want memory intensity in terms of last level cache misses per kilo instruction. And you want row buffer locality in terms of row buffer hit rate, percentage of access that hit in the row buffer. And these need to be collected by hardware because it's very tough for the software to collect them clearly, right? Otherwise, you will need to actually have a lot of interrupts into the software. Okay, the second step is done in system software. Periodically, you can classify applications. So first, you test intensity, MPKI, misses per kilo instruction. If it's low intensity or high intensity, then you take different actions. So there's some question. Is the profiling done dynamically when an application wakes up or statically when computer starts? So you could do both. This paper argues for dynamic profiling because application characteristics change over time. But you could do both. If it's likely that static characteristics will not change, you can do it early on. Okay, of course, if you do it dynamically, then you have a period once the application to memory channel mapping changes, you'll need to migrate the pages to a different channel. You could do it lazily potentially, or you could do it eagerly. Lazy is probably a good idea. As a result, you don't want to be perfect in your mappings. You really don't want to hardwire an application to a single channel without giving the freedom for other applications to use that channel, and without giving the freedom for that application to use other channels. So we want to be flexible, as you will also see soon. But that's a very good question, static or dynamic. Okay, so assume that it's dynamic going forward, basically. So we classify applications into low and high intensity, as you can see over here. And then low intensity, basically row buffer hit rate doesn't matter according to the empirical results. So only for high intensity applications, we classify them based on their row buffer hit rate. Some of them are low row buffer locality, some of them are high row buffer locality. And now we have, as you can see over here, my computer now wants to update itself. and I don't know how to get rid of this. Wow, today we have everything happening at the same time, huh? So I'm going to move this window out of the way because I cannot get rid of it, interestingly. Okay, basically now we have three categories of applications, as you can see over here: low intensity, and then high intensity, low robot for locality, and high intensity, high robot for locality. So now we're going to partition them to different channels. So now there are multiple steps over here. So we basically put in applications over here on the left and channels on the right, and this needs to be general clearly, so we cannot assume 2 channels, 3 channels, 4 channels. We're assuming n channels. So what we do is first decide to allocate a particular number of channels to low intensity applications versus high intensity applications. Based on the proportional to the number of applications in the group. Of course, you can question that if this is a good choice, but this is what we did, and this turned out to provide the best performance in the scenarios we've examined. So it's really, channels are proportional to the number of applications. So if you have, this is really prioritizing low intensity applications, as you can see. Okay, and then, okay, you just assign some number of channels to low intensity applications. Now, how do you partition the channels across these high intensity applications that have different levels of locality? Now, actually, that's based on bandwidth demand. So if this, depending on the bandwidth demand here and bandwidth demand here, you proportionally assign the number of channels. Okay, and eventually you come up with some channel partitioning. Yeah, basically you can come up, look at an example in the paper that's basically runs through an example. I don't think we're going to go through that at this point, since it will take a lot of time. It's just an implementation thing in the end. The high level idea doesn't change. And then the fourth step is assigning each application a preferred channel from its group's allocated channels. Basically, while doing that, we would like to distribute applications to channels such that the group's bandwidth demand is balanced across its channels. We don't want to, for example, we don't want a particular group to oversubscribe channel 3, but not channel 4, right? That's the idea. So we want to balance the demand. So for example, let me give you an example over here. In terms of low intensity applications, let's say you have 3 applications. One has MPKI, misses per kilo instruction 1, another 3, another 4. What we do is we try to balance the bandwidth demand. So here, if you add up the MPKIs, that's one way of doing it. You get 4, and you get 4. Now you balance the bandwidth demand, hopefully. Okay, and then the last step is to allocate page to preferred channel. Now that we've decided which application should go to which channel, we want to enforce that as much as possible. Now we've computed that in the previous step clearly. Okay, on a page fault, what the operating system does is it allocates the page to the preferred channel if free page is available in the preferred channel. Okay, now if free page is not available, we have a new replacement policy that tries to allocate page to the preferred channel. But if it fails, and you can see the paper for more in the replacement policy, we allocate the page to another channel. So as I said, this is not a very strong isolation policy. You're basically isolating as much as you can without destroying performance, right? If you run out of pages in this channel, so you cannot find a replacement candidate in this channel, let's allocate to some other channel, fine. It's not going to be the end of the world. Applications are going to still execute, and they will maybe interfere with each other a little bit more than we intended to, but at least they're not going to get page faults because we're forcing everything to be allocated in the same channel, right? That's the idea. So this is interval-based operation. Basically, in the current interval, we profile the applications, and then at the end of the interval, this classification is done, partitioning happens, and each application is assigned a preferred channel. And then in the next interval, while the applications are running, we enforce channel preferences. So it's very simple. Clearly, you can imagine a design space in terms of how to enforce channel preferences, and I'll let you think about it a little bit. And maybe you'll have questions at the end. Okay, so remember our goal was this, and we discussed our first approach. We didn't go into a lot of implementation detail, but it's okay, I think. That could be part of discussion potentially. So the second approach realizes that this is not good enough for the first approach, so it incorporates some memory scheduling into the partitioning. And let's take a look at what we realize over here. Basically, we observed that applications with low memory intensity rarely access memory. As a result, dedicating channels to them results in precious memory bandwidth waste. So this is kind of obvious, but it's good to see it also. If you have very low memory intensity in some applications, if you get channels dedicated to them, even if you have 100 applications over there, maybe this is a waste because these applications are not going to use the memory bandwidth that's allocated to them, right? So the realization is that these applications should not be allocated channels because we don't want to waste valuable memory bandwidth that could be allocated to some other applications that need that memory bandwidth. And also, these applications have the most potential to keep their cores busy if they're prioritized. Okay, this is a very low bandwidth application. Once in a blue moon, it generates a request. Prioritizing it is a much more lightweight solution. Prioritizing it in the memory control is a much more lightweight solution than dedicating a memory channel for this application and applications that are similar to it. So we would really like to prioritize these applications. And doing so is not bad for their applications because these applications, again, generate a memory request once in a blue moon. They interfere minimally with other applications. It doesn't hurt. Okay, so the next idea after all of these observations is very simple. Integrated memory partitioning and scheduling. It always prioritizes some very low memory intensity applications in the memory scheduler. And of course, this is based on a threshold of memory intensity clearly. And then for all other applications, it uses memory channel partitioning. So the idea is hopefully simple. The low memory intensity applications can send their request to any channel. They're not partitioned, but they're prioritized in the memory scheduler. Whereas all other applications that are not deemed low memory intensity are very low memory intensity. They need to be partitioned using the partitioning algorithm that we discussed, memory channel partitioning. So I think this is a reasonable solution. Now let's take a look at the results. First, methodology and evaluation. So let's look at the hardware cost first. So hardware cost is actually the big plus, one of the big pluses of channel partitioning. You only need profiling counters in hardware. You don't need to modify the memory scheduling logic. And if the profiling counters in hardware already exist, which they don't in many systems, but increasingly profiling counts in hardware are getting made better, although there's room for improvement over there. But basically, then you're free. The cost is free if they already exist, right? So according to our results, you need very small storage cost for a large system, 24 core, 4 channels. And you can read the paper for more details, just for the profiling counters. Okay, IMPS, integrated memory partitioning and scheduling, complicates the schedule just a little bit, but not a lot. Basically, you just need a single bit per request saying whether this request is coming from a very low memory intensity application. And you need logic, of course, to set that bit, right? That's it. And scheduler prioritizes based on that single bit. So there's no sophisticated ranking across many different categories. It's just a single bit that you need to consider while prioritizing. So it's not very complex, as you can see. Okay, so let's look at the methodology. So this is done in simulation. You can see the core model. You can see how big of a system. The paper actually evaluates some sensitivity studies. I'm not going to go in detail. Memory model is a bit old. This is DDR2. Actually, we did these studies in 2010. I think the paper was rejected twice before it got accepted into micro. Maybe I will share the rejection reasons later on also when we get to it. It was interesting. I think the micro paper is much stronger, of course, but we will talk about that when we get to it. Okay, so the methodology is actually, I think, reasonably strong because it tests a lot of applications. It takes 240 multi-program workloads and it categorizes them based on memory intensity. And it uses this weighted speed up metric to measure system performance. This is basically a metric that's used to measure, it basically takes IPC that an application has while it's running together with other applications, divided by application, the IPC instruction per cycle the application has if it were running alone, and it sums them up. Okay, so it's basically a rate of progress kind of metric. If an application is progressing slowly by itself, if it's progressing slowly together, then its speed up will be high enough, right? But if an application is progressing very fast by itself, but it becomes very slow when it's running together with others, its weighted speed up will be much lower, right? It's really slowing down a lot. So basically, it tries to get a good rate of progress across many applications, and it correlates with system performance. Okay, so we're going to compare it to multiple works on memory scheduling. You already know this FRF-CFS. We already discussed this. It's application unaware. Atlas is one work that we had done actually. It prioritized the application with low memory intensity, but it has a full ranking scheme. And then TCM, thread cluster memory scheduling, always as we discussed, it always prioritized low memory intensity applications and shuffles request priorities of high memory intensity applications. So we're going to compare to those quantitatively, evaluate all of them in simulation. And this is what the results show basically. Over 240 workloads, averaged across all of them. This is FRF-CFS. The results are normalized to that. Atlas improves performance a little bit. TCM, the complicated memory scheduling, improves performance a lot. Memory channel partitioning by itself is better than TCM, as you can see. And IMPS is better than everything else significantly. Okay. So basically, memory channel partitioning by itself is 7% better than baseline system, that's FRF-CFS. And IMPS is 11%. 11% is very high across 230 workloads, I think. Even though some people may think it's not as high, but it's not that bad average across many workloads. Remember, there's some workloads that are over here that are not very high intensity at all. As a result, memory is not a problem in them, and you can just look at the paper. So basically, there's significant performance improvement over baseline row hit first scheduler. Let's take a look at this one. So compared to TCM, there's significant performance improvements with very little changes to the memory scheduling logic. Basically, get better system performance than the best previous scheduler at much lower hardware cost. So this sounds like a good idea, right? As you can see. But of course, now you have some software complexity. The software needs to be modified to do the memory channel partitioning. Okay, let's take a look at an interesting figure. The paper has a lot more figures. I'm not going to go into that because we're going to do a review and analysis. But you can look at it. The paper draws conclusions in terms of memory intensity of different applications. Clearly, applications that have higher memory intensity benefit more, but not highest memory intensity, because the highest memory intensity applications are extremely bottlenecked by memory bandwidth. And partitioning, yes, it helps a little bit, but it doesn't help as much as it helps on applications where you don't have this extreme memory bandwidth limitation. Okay, so let's take a look at this interaction with memory scheduling, because it's very interesting, I think. So these are 3 memory schedulers that we use. On top of them, we implement or not implement IMPS, memory channel partitioning, plus the prioritization mechanism of memory channel, of integrate memory channel partitioning and scheduling. So the results are normalized to FRF-CFS, as you can see. So if on top of FRF-CFS you implement INF, you get significant performance improvements. But you get also a benefit on top of Atlas. The lowest benefit comes when you implement IMPS on top of TCM. And the reason is actually interesting. The highest improvement comes from FRF-CFS, implementing IMPS on top of FRF-CFS, because integrated memory channel partitioning and scheduling is designed for FRF-CFS. All of the design decisions are made considering the fact that you have an underlying FRF-CFS memory scheduler to begin with. If you were designing a memory channel partitioning algorithm and maybe an integrated memory channel partitioning and scheduling algorithm, given that your memory controller is TCM, thread cluster memory scheduling, which we discussed earlier, then I would design a different memory channel partitioning algorithm, because TCM does some things to actually distribute the workloads, to do prioritization between different workloads. And if you're using the same partitioning policy you were using for FRF-CFS, I don't think you would gain much. And the results show that also. So basically, the takeaway is your partitioning mechanism should be designed for the memory scheduling policy if you really want to gain a lot on top of a particular memory scheduling policy. Okay, so that's basically the summary of the results also. You can look at the paper for more details, or if you've already looked at it, you can ask me questions. Okay, let me summarize. Basically, the paper is targeting the problem of uncontrolled inter-application interference in main memory. It degrades system performance. It proposes 2 ideas. One is application-aware memory channel partitioning. The idea is to separate the data of badly interfering applications to different channels, eliminating interference. And then it realizes that this underutilizes memory bandwidth for low intensity applications. So it augments the mechanism with integrated memory partitioning and scheduling, which prioritize the very low memory intensity application in the scheduler and handles all other applications interference by memory channel partitioning. And the key result is that MCP and INF provide better performance than application-aware memory request scheduling at lower hardware cost. The key is better performance and lower hardware cost. But of course, there's a software cost also, right, as we discussed. Okay, now let me do some analysis. As you know, strengths, whenever we do strengths, we start with the most important strengths, hopefully trickle down to least important ones. We're going to do this both for strengths and weaknesses. Okay, so basically the first strength, in my opinion, is this is a novel solution to a key problem in multi-core systems, memory interference. And the importance of the problem will increase over time because there will be more interference in the system. There will be more cores and more channels also at the same time. So I think this is probably the most important thing. Novel solution, importance will become bigger. Keeps memory scheduling hardware simple. I put it at the very high because this is all of, previously to this, pretty much all of the works had to modify the memory scheduler significantly. But this work is one of the first that doesn't need to do that. There's fairness via source throttling, which is really concurrent work actually to this, which we may discuss later on. That also throttles the request, but it changes the memory schedule a little bit in the end. Because it needs to actually track of interference across applications. Okay, but basically this is a big advantage of the work, keeping the memory scheduling hardware simple. It combines multiple interference reduction techniques, and this is one of the first to actually do that, again, along with fairness via source throttling, meaning memory channel, this one combines memory channel partitioning and memory scheduling, as we know. It can provide performance isolation across applications mapped to different channels. If you do this actually strictly, now you're actually providing complete performance isolation across different channels, right? And this could be very useful for predictable performance, and also it could be useful for potentially security, because one application that could eavesdrop on the timing characteristics of your request, now it cannot. At least it cannot do it in the memory controller, right? Because you're not sharing memory controllers with that application. It could do it in the cache, of course, assuming you don't do some partitioning isolation in the cache. Okay, so the general idea of partitioning can be extended to smaller granularities in the memory hierarchy. Here we show memory channel partitioning and we stop at that granularity. But you could actually, on top of this, or independently from this, you can partition applications across different banks, across different subarrays, across different, basically whatever granularity that you have in your memory system. Right? It could be mats if they're exposed. So of course, it would make it easier to do this sort of partitioning if banks are exposed to the operating system, if the subarrays are exposed to the operating system. We've already discussed in the row clone review that this is not easy today, right? So basically somebody needs to expose this information. And I think exposing it is easy, of course, but today it's not exposed, so it will require some inertia to actually expose them to the operating system. So in a sense, from this perspective, exposing DRAM topology to the memory controller plus the system software is a good requirement from memory channel partitioning, similar to what's required from row clone also, right? Or at least to take the best advantage of row clone. Okay, so these are, I think, strengths. Maybe you come up with other strengths. Let me know if you do. Of course, you have not had the ability to read the paper so far, but you can guess based on the based on my description that these are strengths, hopefully. On top of this, I believe it's a well-written paper. Again, if you ask me, is this my most well-written paper? I will say no, but it's up on the scale again. And it does, as I mentioned earlier, it does thorough simulation-based evaluation, as you can see from the results. Okay, my computer is telling me again I should do something else. Well, my computer demands a lot from me today. Okay. Okay, so now I'm done with strengths, and I don't see any messages at this point. Let me know if you find any other strengths. Now let's move on to the weaknesses. So we're going to do now a critical analysis, starting from the biggest weakness again. So, and I'm going to put the limitations also as part of weaknesses. Okay, so basically, clearly, this is true, right? Mechanism may not work effectively if workload changes behavior after profiling. For example, you profiled, you found out that the application is low memory intensity, but right after you've done your profiling, which is the previous interval, in the next interval, you change to become high intensity. And this happens basically, too bad, your profiling was not done well, or profiling is not easily possible. You need to do a better profiling mechanism. But if this happens, basically, this gets rid of the benefits or reduces the benefits of the mechanism. And again, the paper discusses some of this. In the end, the paper is really banking on the fact that previous interval is representative of the current interval, right? If that doesn't hold, too bad. But maybe there are some other profiling mechanisms. Now I'm brainstorming a little bit, right? The profiling mechanism used in this paper is time-based or interval-based. So you have a fixed interval, let's say 10 million cycles. Every 10 million cycles, and the paper analyzes some sensitivity to that if you look at the paper. Every 10 million cycles, you profile, and at the end of the 10 million cycles, you do the channel partitioning. Maybe the granularity is problematic, right? 10 million is too long, too short, or not representative. Granularity is always a bad battle in a sense. Essentially, how do you set the granularity is important. So somebody asked a question. It's a good question. Did you think about analyzing the application as sliding window matter? Yes, we did. So a hardware cost increases that way. We didn't evaluate it, but that could alleviate some of the problem, certainly. But you need to make decisions at some point. So sliding window every cycle is probably not a good idea, because that requires a lot of counters for each window. So you can do 2 windows, for example. Again, when you're transitioning between the 2 windows, you still have problems. So it's not easy to perfectly get rid of this problem that I mentioned, but the idea that you propose is a good idea, in my opinion, and that needs to be investigated. In fact, we have some work that's happening on rowhammer prevention that looks at the sliding window kind of approach. You can talk to Giray about that if you're interested. And I see the approach being similar, basically. You have, essentially, whenever you're profiling based on an interval basis, you have this problem. How do you profile? But a perfect sliding window is very costly, basically, because you need to keep statistics for each sliding window. But very good. Keep these ideas coming. Okay. Next, I guess I've discussed enough about this. So I think you can do other things. For example, the application may provide information about phase changes, right? Here we're doing time interval based, but if you have more information, and if it's reliable information, of course, if it's accurate information, maybe the application should say that. Maybe the application should say, okay, I'm going to become really bad at this point, meaning I'm going to become very bad intensity, and I'm telling you that at this point. Maybe those are the times that get communicated to the memory controller and the operating system, and then you take appropriate action. And if this information is accurate, then that's great, right? Then that gets rid of some of that granularity problems. Now the question is, of course, how does that information become accurate? Is it possible to do this for all applications, et cetera, et cetera? Now I'm brainstorming, as you can see, but I wanted to brainstorm at this point because I think it's useful to discuss these issues at the point there where they're raised, as you can see. So basically, my key point is, even though this paper restricts itself to time-based profiling, interval-based profiling, you could imagine other ways of doing the profiling, either application hints, phase-based profiling. There are other phase detection methods that are proposed. Here, we're counting on the fact that the interval is the phase, but there are other detection methods that are proposed when you change, for example, your program counters. That could be a different phase. And there are actually really interesting papers that were published. There's one paper that I would recommend, for example, to people. It was published in ISCA 2003, 17 years ago, that it's called phase tracking and prediction. Essentially, it's doing what I just said, basically. It tries to look at applications and characterize the application's behavior, and tries to basically find metrics that correlate with big phase changes, intensity changes in memory, for example, or IPC changes, for example, and it finds out that instructions that are executed are a good correlator. Not always. Their data access is also important, but this is one correlator that they envision, right? Okay, another question is, a bad CPU schedule in a single core's perspective could degrade the performance during profiling. How would you deal with that? Basically, I think what you're getting at is, while you're profiling, you already have pages allocated. And if it's bad, you degrade performance. Yeah, unfortunately, there is no way to deal with that that's proposed in the paper. The paper basically uses existing channel allocations that were made in the previous phase. So basically, you're stuck with the allocations that are made in the previous interval until your profile changes. That's unfortunate. That's the downside of profiling-based mechanisms, basically. That's why if you have a better way of dealing with this, then let me know. I think application providing hints is actually very interesting. You will later, I believe we will later talk about some papers that provide hints to do virtual memory better, for example, and you could provide hints Like we will talk about the virtual block interface paper that was published in ISCA 2020. I think multiple of you selected as your top papers, but one of you will get to present it. Basically, you can see that an application can communicate information about different memory blocks and how their information changes over time. And then you can make this decision based on the memory block, on a per memory block basis. We call them the virtual blocks. So take a look at that. I think this could be a good discussion. Maybe when we talk about virtual block interface, you can talk about memory channel partitioning also. Okay, does it start profiling from scratch every time? Maybe for more simplicity? Yes, basically. As it's proposed in the paper, the profiling starts, basically the previous interval is your profiling interval. And when you get to the current interval, you restart profiling from the beginning. For simplicity, exactly. Okay, so the second weakness and limitation, and this is a big weakness and limitation, whenever you want to migrate pages, there is an overhead of moving pages between channels. And this restricts mechanism benefits, clearly, right? Basically, you're doing dynamic page migration across channels. And clearly, row clone doesn't solve this problem, right? We've discussed row clone last time. It's good for dynamic page migration within a DRAM chip and within subarrays, but it's useless. In fact, it doesn't even tackle the problem of dynamic page migration across memory channels. And clearly, whenever your partitioning changes, if you need to do many dynamic page migrations, that leads to lower performance. Now, the paper doesn't really go into a lot of detail of this, and this is part of the downsides of the paper also. The paper probably should discuss more of how to do this dynamically better, but unfortunately, there's not enough space in a paper, and there's no more research needs to be done actually to come up with a really good policy. So keep this in mind. Whenever you partition channels, banks, ranks, subarrays, whenever you need to change the partition, you need to move data. And that movement of data may not be very effective. Clearly between channels, it's really bad. Okay, so a small number of memory channels reduces the scope of partitioning, and that's absolutely true. So we can have, for example, 24 cores, 4 channels. Clearly you have a small number of channels, right? It's not like 24 core, 24 channels, because that's a too expensive system. So doing this at the channel granularity is a bit limiting, clearly. That's why I think later works, which I'm going to reference briefly, looked into bank partitioning, for example, because you have clearly many more banks than channels. Assuming that you have 16 banks in a channel, which is actually not, which is actually the minimum today. You can have many more banks by adding many more DIMMs in a channel. Let's assume that you have 100 banks in a channel. And you have 4 channels. Now you have 400 banks, right? You have 24 applications, 400 banks, 4 channels to partition into. So bank partitioning is also a nice mechanism, and later work propose a software-based mechanism to be able to do that. And I think whenever it's used in conjunction with channel partitioning, it could lead to very good benefits. So this could be solved by doing partitioning at a smaller granularity, clearly. Of course, you can go to subarray, and now you have many more subarrays, right? You have 400 banks, let's say, in a system. Each bank has 100 subarrays. That's 40,000, right? 40,000 subarrays to partition, okay? But of course, as you go into smaller and smaller granularities, interference increases. Between 2 channels, there's no interference. Between 2 banks, there's some interference. Between 2 subarrays, there's even more interference, okay? So that's the trade-off, basically. And I think it's really interesting to look at all of those trade-offs. And there is no work to this date, even though there's been a lot of work on partitioning, channels, banks, ranks, whatever you can think of. There's no work, I think, on subarray level partitioning today, which is interesting. I think it's waiting to be looked at. And also there's no work that looks at this holistic partitioning, that looks at a DRAM system as a hierarchical topology and tries to partition workloads or allocate pages in a holistic way to different channels, banks, ranks, and subarrays. So there's some work that remains to be done. Of course, I think this is not an easy task because there's a lot of complexity, a lot of trade-offs, but maybe machine learning is actually a good approach to solving something like this. Maybe you set up a machine learning model to allocate the pages of applications to different granularities of mapping. and then the machine learning model learns it automatically. Of course, it's easier said than done, but I believe there's a lot of opportunity for doing this, and maybe it can be done. And if it's done, then actually it could be much more effective than individual channel partitioning, rank partitioning, bank partitioning, and subarray partitioning mechanisms. Okay, so this is important. Load imbalance across channels can reduce performance. So remember, we tried to eliminate this load imbalance by ensuring that applications with low memory intensity don't get allocated, over-allocated memory channels. And we also try to balance the load, if you remember my description. But again, in the end, you can end up with load imbalance, meaning that some channels may get a lot of memory bandwidth demand, and some channels may get much less memory bandwidth demand. And clearly, this is not good, right? Because some channels will be oversubscribed in terms of the memory bandwidth that is provided by the channel. Some channels will be undersubscribed. And that's, I think, a fundamental issue with memory channel partitioning. You could prevent it as much as possible by having good policies, good clustering mechanisms, good, as many of you discussed, good profiling mechanisms that are not wrong or that are not inaccurate or that can adapt to the changes very quickly. But in the end, there will be some load imbalance because fundamentally you're partitioning. Okay, and this paper addresses actually this and compares to another mechanism, but there needs to be more that needs to be done. So you can read the paper. These are the biggest weaknesses, I think. As you can see, it's really about the weaknesses of the mechanism in the end. I don't believe there are big weaknesses in the idea itself, because idea actually opened up a lot of research directions and idea directions, but the mechanism clearly has some weaknesses and limitations. The next thing is, adoption. Let's take a look at adoption weaknesses. So clearly this is a solution that cuts across the stack, right? Similar to row clone. Basically, it's a software-hardware cooperative solution, and it might not always be easy to adopt. And that's true, of course, right? There's not much to do about this. Other than trying, I don't believe it's as hard as row clone, because row clone is a computation or data movement mechanism. It has issues with cache coherence, etc. This doesn't have issues with cache coherence. It doesn't have issues with data reuse, etc. It has issues with migration, which is a bit different. Clearly, over here we discussed, but it's not as hard to adopt, but it still is not as easy as a pure software or pure hardware solution. But I believe it gets the best of both worlds, hardware and software in this case. Okay, another weakness, now we're getting into rat holes potentially, right? Evaluation is done solely in simulation, and that's correct because we didn't have a system where we could actually partition channels easily. Although while we were doing this work, there was a lot of work also going on in reverse engineering memory mappings down to the bank level. So we could potentially use that work, but it was concurrent. We actually started this work in 2010, early 2010. It got published in 2011. Actually, we started this work in 2009, I think. It got published in 2011. And there are papers in 2010, 11, 12 that look at reverse engineering mapping such that you can know where a bank, basically you can know where a row goes in the ETH. So we could have actually done better after those works, after knowing those works, but while we were doing it, we didn't have access to those works. And also, I think there's another reason. We couldn't do propose the same mechanism because these counters that I discussed don't exist in hardware. So we would have had to fake the existence of those counters in some way or collect that information in software in some way, if it's even possible to do that. I don't believe it is actually. Especially the row buffer hit rates individually when applications are running together with each other, because you need to collect the row buffer hit rates unhindered by other applications while you're collecting this information. And that information definitely is not collected in existing memory controllers. So we wouldn't basically evaluate the same idea. It has to be an approximated form of idea that does the best, given that you cannot collect all of that information in software, right? That's the idea. Okay, so basically, I don't believe this is a completely fair concern, but of course, if you could evaluate it in simulation, it would have been always better. But again, it requires a lot more work, including the reverse engineering, which we didn't have exposure to. Okay, there's some question over here. Let's see. you previously said that channel partitioning could be beneficial to improve security because the security critical application could be isolated to the one channel. Did I understand that correctly, that your paper partitions the channels exclusively on their memory intensity and not upon other metrics? So no, basically I said that this could potentially be an idea building on the general memory channel partitioning idea. So our paper doesn't really provide any security. It's not even concerned with security at all. It's really all about performance. But I think if you can partition channels intelligently, this could help security as well. And this could be the brainstorming part, potentially. Maybe there's a way actually you can discuss in the brainstorming part about this. And I believe actually partitioning, isolation is a good thing for security. But of course, if you're doing that isolation, you really need to be isolating. You cannot be sloppy about it and say, okay, I'm isolating, I don't know, 85% of the time, but 15% of the time, my pages are not isolated. Somebody who is intelligent, creative, will figure out how to actually make use of that information with those 15% or 5% or 1%, whatever it is, and then basically do timing analysis in some way, in my opinion. So I think full isolation is much better for security, but that's a good question. Okay, another question over here. Does it make sense to consider concurrent applications which are distributed over the cores but operate on the same memory in the context of this paper? I'm not sure if I completely understand this question. Maybe you can clarify it while I'm continuing. I didn't understand what distribute over the cores mean. Because basically the paper considers applications that are running across different cores, but even if they're running on the same core, it wouldn't be any different basically. Of course, when you're running on the same core with some application, you have other interference problems, right? So maybe you can clarify your question if it's not answered based on what I said. Let me know. Okay, let me go into the next thing while maybe you're actually doing that. So evaluation doesn't consider multi-chip systems. So that's true. Basically, if you have two chips that are connected and they're sharing memory, which also happens. This is a completely NUMA system, non-uniform memory access system. You may actually get applications from one chip interfering with applications from another chip, and that happens. And if you want to especially scale a large multi-core system, this happens a lot. Maybe we could have evaluated this, but it would be a huge overhaul of our infrastructure to be able to do that. But I think looking at multi-chip systems is even interesting because this idea may be even more powerful when you actually do this partitioning. So you can potentially do a page allocation that's NUMA aware, which is already done in Linux today, actually. But we want to go even beyond that. We want to do it per channel partitioning. And I think with multi-chip systems, you can actually get even more benefits. Okay, but clearly the evaluation is not done, so there's no conclusive answer in the paper. Okay, the next question is definitely a rat hole. Are these the best workloads to evaluate? And clearly not, basically. My answer would be clearly not, because there are other workloads in the world that are interesting. If you ask me that question in hindsight right now, maybe we should have evaluated big neural networks running together with other big neural networks and interfering with each other, and then basically making decisions on safety critical information that you're trying to infer using those different big neural networks. And if they interfere with each other, maybe the decisions are much more delayed than it could be, right? I would evaluate a scenario like this. But of course, we're talking about 2009 to 11, and neural networks were not a big thing until as late as 2012, when the seminal paper from Jeff Hinton's group from University of Toronto was on ImageNet was published and showed that you could do these deep neural network inference using GPUs on this ImageNet data set that they also released at the time. So clearly, these are not the best workloads to evaluate, perhaps, because these are random mixes of multi-program spec workloads. But that said, they're not also bad workloads to evaluate, because that is a general cloud computing or multi-programming type of scenario that's being evaluated. But if you ask me how much would this delay the inference if you're consolidating 10 different neural networks on your next Tesla car, and they're all making life-critical decisions, the answer is I don't know. But you can see it's good to think about these applications, but this should not really cause a rejection of the idea because the idea fundamentally is applicable to those workloads also. This is just an evaluation issue. Let's apply the idea and see how beneficial it is in those workloads, basically. Somebody can do that evaluation 5 years down the road when they may find that, okay, these neural networks are really exciting. Let's see if this idea makes them better. Okay, so basically my point is try to avoid rat holes clearly, right? And benchmark is always a big rat hole. Okay, so I think your fellow student has clarified the question. I'm not sure whether it's a misunderstanding on my part, but I thought there might be some stalls created if there's a parallel application, depending on the different parts processed on the different cores, if the schedule is never. So okay, that's a good point. Basically in this paper doesn't consider parallel applications, if I remember correctly. Now, if there's an evaluation of parallel applications in the paper, let me know, of course. But I don't think we did evaluate parallel applications. So basically, the paper considers only multi-programmed single core applications. But I think it's generalizable to parallel applications with the same way. But we leave it to future work to actually look at parallel applications. So for example, if an application is generalized, uses 10 cores, you just need to aggregate the statistics from those 10 cores, basically. It's just that we didn't have a good infrastructure to evaluate those applications. And evaluating parallel applications using computer architecture simulators is not easy, actually. So now I think we're on the same page and your question's answered. That's good. Okay. Okay, so clearly that's not a rat hole, I think. Does this work for parallel applications is actually a good question. And the answer is it could be made to work, but this paper doesn't make it work. And intuitively, I think it should be made to work, but we don't know the results. So in the end, it's a limitation and weakness of the paper. It doesn't evaluate parallel applications. So it should be actually on the previous slide where you talk about limitations and weaknesses of the paper. So very good point. Okay, so let's talk about some thoughts and ideas. So clearly, we're not going to do the other paper that I envisioned to do. But what I'm going to do probably is maybe either cover it next week or we will release a video for the other paper. So let's spend some time on this paper and maybe we can end early or we can keep the discussion going as long as it may be going. So let's talk about extensions. These extensions I kind of talked about actually. Can this idea be extended to different granularities in memory, not just channels, but banks, subarrays, etc., mats, ranks, etc., whatever granularity you have that makes sense to partition? And the answer is yes. I will mention some works later on. There's a PACT 2012 paper. It's called Software Bank Channel Partitioning, I think, that looks at this and shows good benefits on real workloads because they actually went and reverse engineered, essentially reverse engineered the mappings such that they could do this bank partitioning in a real Linux-based system. There's another paper in HPCA 2012. These are early papers. There are many papers that come after that, of course. I'm not going to provide you a long list of literature for this one. That paper shows bank partitioning, channel partitioning at the same time also. Okay. The next extension is, can this be extended to provide performance predictability and performance isolation? So this is along the lines of the security question one of your fellow students asked, right? And because performance predictability and performance isolation requires applications to be mapped exclusively to channels, or at least those applications that require performance isolation guarantees should be mapped those channels, right? But again, you don't want to lose efficiency a lot, performance a lot. So maybe you map the applications that, if you have one performance critical application in the system, maybe you map it to one channel. Okay, so this is clearly not a methodical solution, but this eliminates the interference, at least in the memory controller, from other applications, right? So that's one place to start. Clearly, there's more work to be built up on this, but I think the idea can be extended to provide performance predictability and performance isolation. Maybe not to all applications if they all demand performance isolation and performance predictability guarantees, right? Okay, so how can it be combined with other interference reduction techniques? And there are a bunch of methods like source throttling. What does source throttling do? Basically, if the memory system, if there's a lot of interference in the memory system, it basically throttles the core of the application, throttles the core that's generating too many memory requests causing the interference. And it does methodically. It's published in this S+ work that we had done. It actually received the Best Paper Award in this Support S+ conference, which is an interdisciplinary conference. As you can see, it's architectural support for programming language and operating systems. And it's a nice approach. Again, it keeps the hardware complexity relatively small, but it requires a lot of performance counters, much more so than memory channel partitioning. So I believe it could actually be done combined with source throttling methods. And it's a good idea to look into it. And there are some papers that look into it briefly, but I think there needs to be more work done in this area. How do you combine different interference reduction techniques together? Clearly, we talked about thread scheduling. Well, we talked about memory scheduling methods that are thread aware. Clearly, MCAP can be combined with them because IMPS is an example. But there are also higher level thread scheduling methods, right, at the operating system. Maybe you're careful. You have this feedback from your memory controller in terms of memory intensity, robo for locality, and the characteristics of different applications. And based on that information, you don't only allocate memory pages from different channels, but also you decide which applications are scheduled together on the cores, right? And this is probably a good idea to look into. There are some papers that look into this. I'm not very comprehensive over here, but they're referenced in the paper that I presented. So MCP clearly can be combined with these scheduling methods also to achieve better interference reduction. Okay, we already discussed this, but can this idea be evaluated in a real system and how? I think today, yes, but at the time we did the work, we had to reverse engineer, and we didn't have the means to reverse engineer at the time. Other people did that. So today, I think it can be evaluated on a real system. And it'd be nice to see it actually. Actually, the bank partitioning paper that I mentioned in PAC 2012 is already evaluated on a real system, and they do some channel partitioning as well, and it shows that the results are good overall. So you can take a look at that. Okay, so are there any questions? Okay, there were quite a few questions. That's good. I guess there's one more question that I just saw. Is there any known malicious applications taking advantage of this mechanism for degrading performance, inducing too much traffic on a specific channel? That's a very good question. So I think this is good critical thinking, basically. I mean, of course, I don't know. I don't know of any work that has attacked these solutions, frankly. But it's a good direction to attack the solutions that we are actually proposing. There could be, I think, if someone knows the inner workings of how this channel partitioning operates, it could cause the system to over subscribe a particular channel, for example. I believe the system, this mechanism is not robust to attacks, basically. If you ask my personal opinion, that's what I would say. I don't think this mechanism is, the way it's described in the paper, is robust to attacks at this point. That said, I think attacks are not as easy as they would be in memory performance attacks, for example, which we have done. But it's not, I don't think it's prevented. So there needs to be more work to be done to implement a more robust mechanism that's not vulnerable to this sort of attacks. So very good question. It's good to think broadly as we have discussed, and I'm happy that you all are doing that. Okay, next question. Wouldn't this approach be only useful for GPUs, but also for CPUs nowadays? Oh, not only. Okay, good. With server. So absolutely. I think the approach is good. Approach is basically fundamentally applicable to any system that has multiple channels. And GPUs are actually today have lots of channels, and GPUs also are running many applications, many kernels at the same time. Clearly, we didn't evaluate them at the time, and we don't also discuss the strengths. But I think the idea is much more generally applicable than CPUs. It's really applicable to a heterogeneous system, including GPUs. So that's also a very good point. Actually, I think there was some work by NVIDIA. I don't remember, frankly. There's a multi-chip module work by NVIDIA in 2016 or 17 in one of the top conferences where they actually did partitioning of channels to actually improve performance. You can take a look at that, and hopefully my TAs, Hayu and Konstantinos, who are the scribes today, are going to look for them. Okay, there's also a work that we have done personally, actually. This was published in ISCA 2008. My student Nandita, it was part of her PhD thesis. basically it's called the locality descriptor. What it does is essentially it does memory channel partitioning. And the way it does memory channel partitioning is by getting information about GPU applications. Basically the GPU programmer provides what's called a locality descriptor with each data structure. And this descriptor provides information about the locality characteristics of the application. For example, is it very intensive? Is it streaming? Is it random access? You can imagine other things. What kind of cache hit rates do I expect? Is this going to be hitting in the raw buffer frequently? So somebody actually provides that information, and a GPU programmer is a good person because usually they know about the data structures. And this information gets communicated, and also they provide sharing information across different kernels in a GPU, different threads in a GPU. And then this information gets communicated to the GPU system and the hardware. And this locality descriptor mechanism allocates memory channel to different data structures or different applications in a way to minimize interference and maximize locality. So I would recommend looking into this locality descriptor paper that we have published in ESCA 2008 that gives a way of doing memory partitioning in a nice way. So maybe someone can actually put the paper link, one of my TAs perhaps, paper link onto the chat so that people can see it, because that's actually a really good way. I haven't thought about it that way until this point, until you raise the question. So in a sense, it's kind of done for GPUs, of course, in a different way than what was envisioned and proposed by this paper. Okay, so I don't see the link in the chat window, but maybe someone is actually getting it. And please provide these links in the chat window. In last year's seminar, actually, we had a good way of providing these links in the chat window. People could click. Of course, we're going to have actually these posted also online. So people are taking notes, and we'll post some of these papers online. It's always good to, again, as we mentioned in an earlier lecture, while you're reading a paper, you discover that there are other papers to read. Whether they come before this paper or after this paper, it's not that important, I think. It's always good to read broadly so that you can actually see how things have changed. I will also mention one more thing that does memory channel partitioning. This does actually bank partitioning. This is, again, a work that we have published in ISCA 2018. It's called XMEM, Expressive Memory. It basically provides again, solution for applications expressing their memory properties to the hardware. And in this work, we evaluate data structure aware allocation to different banks. So we basically look at bank partitioning on multi-core systems. Again, somebody can put up that work on the chat window, or hopefully they will be made available in the yeah, what was I saying? On the course website. Okay, I think there's another question. Do you know how widely these mechanisms are already distributed in real world systems? So actually the answer is I don't know. I know people implement memory channel partitioning, so I know this is implemented in real life. Clearly there are papers that actually also implemented after our paper. They also implemented this idea in real life. But I know that there are works that have implemented this in real life, but I don't know how widely they're distributed. So thanks, Nika, for posting XMEM, but please post locality descriptor also. You can also post it on my website. I think you have a PDL CMU link, which is good, but my website also has them. Okay. Okay, so good. I think there are no more questions, so let's keep going. Okay. So let's talk about takeaways. So let me give you the takeaways. So basically, this is, at the time it was published, this is a novel method. It was a novel method to reduce memory interference. It's simple and effective. It's hardware software cooperative. So these are, I think, good takeaways. I like the simple and effective part. And actually, even at the time, it had good potential for work building on it to extend it. I mean, I didn't do a very comprehensive survey on it. We always wanted to write a survey on memory controls with Lavanya, my PhD student, but we all got busy, so we never wrote that survey, unfortunately. So as a result, we don't have a comprehensive analysis of all of the work that has built on it. as we had with row colon, for example, and as we have with row hammer. So clearly, it can be extended to different structures, different metrics, performance isolation, for example. Somebody said GPUs, different kind of systems. And multiple works have already built on the paper. And I already mentioned bank partitioning, but these works that are on the chat window right now are actually also built on the paper. And I think the last one is also important. It's an easy to read and understand paper. Okay, I think we've discussed a lot, but there's more open discussion points. Basically, the discussion starters. Again, this is very generic. I would recommend when you actually talk about things, think about less generic discussion starters. For example, can this be applied to GPUs? Can this be applied to heterogeneous systems? Can this provide secure performance isolation? Can this provide security isolation, etc.? So it's good to have these. But let me go through these. I guess, are there any other thoughts on the previous ideas that we've discussed? I don't hear anything. By the way, feel free to speak up also. I mean, you can speak up. I don't know how our Zoom will sustain the speaking up, but you don't have to, you don't need to feel compelled to write things because writing is sometimes slow. In the past, we had discussions where people spoke up, so it's perfectly fine to take over the window microphone and speak up. I assume you can unmute yourself, so that's not a problem. So in future discussions, I'd like to see more of that. Okay, I don't hear anything or I don't see anything, so I'll keep moving, but feel free to speak up or write something. Okay, how practical is this? Clearly, this is very practical. Basically, there are implementations of it that exist. Maybe not with exactly the same performance counters we envisioned, but with some sort of performance counter. So the general idea is very practical. Exact implementation may not be the most practical, clearly. Will the problem become bigger and more important? And I believe yes, because interference is increasing. As people said, as folks said, GPUs are becoming, different types of computing units are actually sharing the memory. And as a result, memory interference is becoming a bigger problem. Number of channels is increasing. Number of cores increasing. So I believe the problem will become bigger and more important, clearly. So Juan also posted the NVIDIA paper, so you can take a look. I'm not sure if it was that paper. I think that could be also, I'm not sure. But there's also this multi-chip module. So if you search for multi-chip module NVIDIA, I think you may be able to find it. Okay, I don't unfortunately remember the full title. I think Iman Ibrahimi was one of the authors. I will say that much, but even that I'm not certain about that. Okay, will the solution become more important over time? This is a good brainstorming topic. I believe it will, because I think this is a very fundamental solution, because channel partitioning, it's intuitive, fundamental. If you can do it, why not do it, right? And I think as systems scale bigger and as the channels increase, I think these, so with a very few number of channels, the solution is difficult to employ. If you have only 2 channels and 12 applications, you're very constrained. If you have 100 applications and 16 channels, okay, you have a little bit more freedom right now. So it's good to consider this basically. So clearly applications are increasing, but also channels are increasing. Okay, are other solutions better? This is a very general question. Clearly, it's good to be targeted if you ask this question. I don't know, clearly. I mean, clearly a combined solution would be better, in my opinion, if you combine source throttling, memory scheduling, and also partitioning in a nice way such that they integrate well with each other. I think that would be nice. But again, there are no good solutions that are published that does what I exactly said. So I think it's good to think about maybe specific solutions. I mean, so it's not clear to me if there are other specific solutions that are better. So clearly the solution doesn't work the best for all applications. It's a general purpose solution. There could be, or all workloads, let's say. There could be some applications that do better with memory scheduling. There could be some applications that do better with this solution. There could be some applications that do better with source throttling, right? In the end, it's very much application and interference pattern specific in terms of which solution does better. So getting the best of all solutions would be nice if possible, but that's a research problem basically. Okay, last thing, again, we don't need to answer all of these, but it's the solution clearly advantageous in some cases. Yeah, I can see actually some cases where the solution clearly advantageous. You have 2 applications, 2 channels, you can do it, right? Or small systems where you're not running many applications. Again, channel partitioning could lead to much better performance. Okay, so I think we're almost done. I mean, I didn't copy some reviews over here because I didn't have time, but I will give you some anecdotes in terms of what happened to this paper. Initially, again, this was not immediately accepted. We submitted to ASP+, for example, where I think this is a great fit, architectural support for programming languages and operating systems. Interestingly, it was rejected from ASP+, because people didn't find there was a lot of software content, which is interesting to me. That was, I think, an unfair reason for rejection. Because I think who cares about how much software content you have? And there's enough, I think, operating system content over here. And it's in the spirit of the ASP+. Basically, it's basically architectural support for operating systems. Maybe even programming languages, but I don't want to stretch it that far. So basically, it got rejected for that reason from ASP+, which is really interesting because when we had submitted earlier to ISCA, we got the comment, there's too much software content, this would be a better fit for ASP+. So you can basically reject any paper by deferring to some other conference because for whatever reason you don't want to accept it, right? But in the end, it was published at Micro, as you can see, which is a top conference. And over there, even then, we got comments saying that, this is basically, it's a hardware software cooperative solution, clearly. And some people, unfortunately, some reviewers are not comfortable with those solutions. They basically say, oh, this is too much hardware, too much software, send it to some other conference as a result. And even at Micro, we got similar comments saying that, oh, maybe this is a better fit for ASP+, where we got rejected from Ardi for reasons that it was not a good fit for ASP+. So you can see that these sort of solutions that span across the stack, while they could be very, very useful and beneficial, and they definitely contribute to science, they're not as easily accepted in the first place. And row clone, I've already given you that example. Row clone clearly cuts across the stack, and that was also not easily accepted. And if somebody presents the Ambit paper, which is doing bulk bitwise operations in DRAM, I'm not sure if it was selected. Several of you were interested, but because it was presented many times in prior incarnations of the seminar, I decided, okay, let's pick some other paper and let's give Ambit some time until it's picked next. But if I recommend looking into it, some of you actually will become familiar with it because some of you will review compute DRAM, for example. But Ambit paper, which actually proposes bulk bitwise operations in DRAM by modifying the DRAM circuits, it spans all the way from circuits to algorithms. So it's really truly cross-stack. It shows that by modifying some of the algorithms in applications, you can get much better performance by doing all of these circuit level modifications. So there's modifications at the circuits clearly to do bulk bitwise operations in DRAM. There's modifications to the algorithms. There are modifications to the ISA, instruction set architecture. There's modifications to some mapping mechanisms, memory allocation, etc. So there's modifications to logic. So basically there's modifications all across the stack. And this paper clearly has a lot of impact after it was published finally in 2017, Micro. But we first actually submitted to in 2015. So it was rejected 4 times, I believe, or maybe it was rejected 3 times, give or take. Basically, it's 3 times or 4 times too many, in my opinion, because the idea and everything interesting was there in the first place. So basically, if your work is somewhat disruptive and spans across the stack, I think Ambit is much more disruptive than memory channel partitioning, clearly. But there's some resemblance that they both span across the stack, even though Ambit is much more intrusive. There's clearly, it's easy to resist this kind of work, and it's easy to dismiss, saying that, oh, this is too complex, this spans across the stack, it's too much OS, too much software, too much hardware. In fact, in the Ambit paper, it says too much circuits. We got that comment and it was rejected from ISCA, saying that it was too much circuits. This is an architecture conference. Why are you sending it to an architecture conference? This is all about DRAM circuits, which is not true, actually, if you read the paper. But basically, you will get all sorts of comments because I think people are not open-minded. They're not fair, at least some people, not all people, of course, clearly. But because some people are not open-minded or fair, or they think of research as they do research, meaning they have a set way of doing research. As a result, they cannot consider, or they're not open to other approaches to research. Basically, I think of this as the horse analogy. You're a horse, you have the blinders on, right? Some people, probably you have seen horses with blinders on. You cannot even see, right? Or you cannot even see beyond some angle, right? You have your blinders on and you just see what's right in front of you. And this is where actually video could help. Basically, I'm going to imitate what a horse with blinders on. That's basically what it is. A horse has blinders on, right? It cannot see anything beyond those blinders. As a result, it's not open to anything beyond those blinders, right? So I think some of these reviewers are like these horses with blinders on, and they make very biased and unfair and non-constructive comments by dismissing some ideas that span across the stack, just because it's not their way of doing research. But this doesn't mean that it's not a way of doing research, right? Clearly. So I think whenever you're reviewing papers, keep this in mind. It's always good to say, okay, this spans across the stack, so adoption may be difficult. That's a fair comment, right? Clearly, if something spans across 10 levels of the stack, all the way from circuits to algorithms, yes, immediate adoption will be difficult. But that's not a reason to reject the idea from the get-go, because if you actually don't publish it saying that adoption will become difficult, then you're guaranteed that adoption will be difficult. In fact, impossible, right? So let's wait and see. Basically, that's a good answer to that sort of comments. Yes, adoption is difficult, no question about that. But in order to have some progress, you should not be immediately bound by these adoption issues and dismiss every single idea because its adoption is difficult, because this is research in the end, or dismiss every single idea because it's too costly from your perspective, right? So it's good to, again, I go back to our prior discussion on reviewers and review fairness. And for you, it's also important because you're reviewing papers in this, in the end. So it's important for you to be fair. It's important to realize that you don't know everything necessarily. And as a result, for you all, I recommend to be fair, to be open-minded, to be open to new ways, different ways of doing research, to realize your own biases, because all of us are biased, and don't do double standards. I think I see a question over here, which brings me to double standards also. So somebody, I think that's a good question, basically. Honestly, since the reviewers are anonymous and the writers of the paper aren't, how much politics is involved in the process? So, okay, so let me correct one thing. In many conferences today, reviewers are anonymous and authors are also anonymous. That's not true for all conferences, but people have figured out that there's a lot of politics if actually authors are not anonymous also. So it's, in many conferences today, it's double blind. So that gets rid of some politics, but it doesn't get rid of all of the politics. Let me put it that way. Because, I mean, politics doesn't get caused only because you know the author names, or you have some animosity to this author, or you're jealous against this author, or whatever. It gets caused because of that. That's part of it. But politics also happens because you're also doing research in some area, right? And you have your set ways, and you want to prevent other people publishing in that area. And this is a really terrible form of politics, clearly, right? That happens regardless of whether you know the author names or not. And I've seen that happen clearly. This is really biased. It happens in science, as I mentioned. If you read Structure of Scientific Revolutions, you will see this. In the past, people used to kill other people so that some of these ideas don't get disseminated because they're blasphemous, right? That happened, right? If you claimed, as I mentioned at some point, if you claimed the earth was revolving around the sun, that was blasphemy. And in a sense, that's a terrible way of reviewing an idea. He just basically says, oh, it's not my religion. Okay, anyway, I don't want to take this to more levels, but basically keep in mind that humans are involved in the process, and there are many reasons why politics may come in. And again, this is good for you to understand because you're going to present these papers not here, but in the future, you're going to present these ideas to some people who are going to make decisions, right? And they can dismiss your ideas for whatever reason. So it's good for you to be exposed to the fact that there will be people not necessarily fair, not necessarily unbiased. They'll be validating your ideas, and it's always good to keep this in mind. And this is going to happen regardless of wherever I go, in my opinion, as long as you're going to interact with humans, and as long as you're going to propose ideas. So it's good to develop strategies to fix this, and it's also good to recognize these problems early on, and and somehow improve yourself such that you can present the ideas in the best ways that are potentially receivable by your audience. So knowing your audience can help. Clearly, if you're describing these ideas to a known audience, they know you, you know them. I think the amount of politics is less, frankly. They can directly tell you, okay, this is crap, right? And when that happens, then there's opportunity for good discussion. Then you ask the question, why is it crap, right? But it's very disturbing that some of this is happening in science, as you know, right? Because what's happening is the reviewers are anonymous, and they're not held accountable for rejecting a paper in the end. Whereas you can easily hold someone accountable if their reviewers are known, right? I'm not suggesting that's the solution. I'm suggesting the solution is probably adding more accountability into the system. Okay, and there are potential ways of doing that, but clearly that's beyond the scope of what we're discussing. Okay, I see a lot of questions, so I'm going to answer them before dropping off. So let me see. There's one question. Somebody has to leave. I will watch the rest of the lecture later on the recording. Thanks for the interesting presentation. That's good. I mean, yes, none of this is required. As you know, you can leave anytime. You can watch the recording. Even if you don't watch the recording, I don't think you will lose anything related to the seminar, but you may gain something, hopefully based on life lessons in a sense, let's say. Okay, let me take the other question. Why improving even just a little bit an aspect of a programmatic paper isn't enough to accept a paper? This is always better than nothing. So why are there papers solving at least partly a problem which are rejected? Yeah, so I think this is a valid question. I think you say I answered it. I'm not sure if I answered it, but basically I think, yes, I think people are way too negative, let's say. As a result, they don't want to necessarily accept some papers. And sometimes, regardless of whatever the papers have done, unfortunately, I've seen this actually. People unfortunately grow negative for whatever reason. Some of it is political, some of it is not political, some of it is biases that they have. As I said, some of it is because they don't know enough, and they don't know that they don't know enough. So some of it is malicious, clearly, but some of it is not malicious also. And as a result, people reject papers, even though they may have valuable contribution in them, even though that contribution may be incremental. And again, I think, I mean, Einstein's general theory of relativity was incremental after he published special theory of relativity, right? Everything is incremental from some perspective in the end, right? So it's good to take things with a grain of salt and not be overly negative for whatever reason. Of course, when this is malicious, it's terrible. And clearly there's a malicious aspect to it. If you read the structure of scientific revolutions, you will see it. And I see it also a bit. Having done research in the field for almost 2 decades, I know that clearly there's a malicious aspect, but there's also a less malicious aspect also. Some people reject papers maliciously because they have a gain. They have something to gain from rejecting that paper or this paper or that paper. And sometimes they even know the authors of a paper, because you can guess sometimes, right? Sometimes you can guess because there's only one group in the world who can do research with an infrastructure that's similar to us, for example. So you can guess the authors of a paper sometimes based on the infrastructure and the methodology that's used. So it's not double blind. Actually doesn't fix the authorship, authors unknown, authors known problem. Okay, anyway, who may review papers? Anyone or selected people? That's a good question also. I mean, some of you are not aware of course, how this process works. But usually in top conferences, there's a program chair. The program chair oversees the review process, and they essentially form a program committee. These are supposed to be experts, a wide range of people who know hopefully enough about the field that they get assigned to the committee, and then papers get submitted. Sometimes hundreds of papers get submitted to these conferences. Like 800 or so, let's say. Some conferences receive even more. I think NeurEPS receives lots and lots or more, maybe on the order of 10,000s. because machine learning is hot. So there's a lot of interesting stuff that's going on over here. But basically, based on what the paper is about, ideally the program chair should do due diligence and try to assign good reviewers to the paper, such that they know that the reviewer will do a good job, meaning they're trustworthy and they've done a good job in the past, such that the reviewer is not biased, such that the reviewer doesn't have a conflict or bias against the authors or for the authors, right? Basically, the reviewer needs to be neutral, right? If I've done this program chair duty for many conferences, and that's essentially, those are the principles I try to abide by as much as possible. Of course, the reviewers will not know the authors, but the program chair knows who's the author and who's the reviewer. And the program chair doesn't communicate that information between the author and the reviewer, of course, but based on that information, they need to make a fair decision such that the reviewers will not be biased either positively or negatively. They should be neutral. They should evaluate the paper, not the authors. And hopefully, and then, so the program chair needs to be careful in the sense that they don't cause these political issues to be exacerbated, in a sense. And of course, they need to be experts. They need to get expert opinion that's not biased. So that's how the allocation gets done, basically. So that's another good question. Why is it then anonymous at all? You're opening up a can of worms, basically. These are really good questions, basically. If these are experts, they should have the confidence to stand behind their comments, shouldn't they? Yeah, I agree. But I think this is a double-edged sword, basically. There are other issues, I think, that anonymous. So I think basically, I think you're referring to why should the reviewers be anonymous, right? And I think I mostly agree with you, actually. I think a lot of problems would be solved if the reviewers were not anonymous. Then they wouldn't produce, hopefully, crappy reviews because their reviews are published online, right? With their names on. Hopefully they will not do that because something is at stake over there, clearly, right? So I think reviewers become anonymous reviewers not being anonymous is useful, in my opinion. But I mean, there could be some unforeseen consequences. So that's why I think this needs to be thought about in more detail. Community is in general against making these reviewers anonymous. Partially, in my opinion, because some reviewers want to be anonymous. There are some bad reasons for it, as we've already discussed, but there are some good reasons for it also. For example, let's say that you're a junior researcher, you're an expert on a topic, and you review some senior researcher who is very well established in the field. And you want to reject it for a valid reason. Now, it should not happen in a perfectly meritocratic field. In a perfect meritocracy, the thought of repercussion of a negative review, meaning a reject review, that's fair, should not really be problematic, right? But unfortunately, we're all humans and the world is not perfect and not everyone is fair. And this junior researcher either may change their review such that it's not fair and it's biased now, even though they may think otherwise, because they don't want to be exposed to the negative consequences of some senior person who may be known to be really harsh and annoying and unfair. So this sort of thing can happen, right? We're dealing with humans at this point. Not everything is perfect. As a result, this is the argument for anonymity of the reviewer, basically. So there is a benefit you can see, because I think these are not easy issues to solve. Because I don't think you can expect everyone to be fair by just dictating that, okay, everyone be fair today. Clearly, these are issues that are beyond science at this point, because if we expected everyone to be fair, the world would not be in the situation that we are in right now, right? You can see how bad 2020 is and how low in terms of some discussions that are happening in politics in some of the most advanced countries in the world are, right? It's amazing. So clearly, by expecting people to be fair and reasonable, they're not going to become fair and reasonable. But you somehow need to add the checks and balances into the system such that they're accountable. Of course, the question is how to do that. clearly in all the biggest democracies in the world, there were some checks and balances, and none of them seem to exist anymore. We will see. So checks and balances can be avoided also, as you can see. So these are actually issues that span beyond science, as you can see. But it's terrible when they happen in science, clearly. Okay, let's look at the next question. I think maybe I'll stop after that. So somebody said, okay, okay, I get why anonymity can have a benefit. Okay, you're welcome. And the next question is important. What kind of value does a paper earn when being accepted? Basically, this is a good question, basically. So acceptance at a major venue is actually is a big deal, basically. These venues don't accept a lot of papers. They're very selective. A venue like ISCA, for example, there are some people in the world, some people in the industry, for example, they don't have time in the world, but they want to read some papers. They have limited time, and they basically need to select which ones to read, right? They're not going to be able to go and read all papers from all conferences. So because of the reputation of some of the top conferences, they go and read just the top conference, let's say, or just 2 top conferences, or they select 5 papers from the top conferences, right? In some way. So that gives you an immediate value attached to being published, right? So if you're not published in a top conference, well, these people, basically you're not reaching as wide of an audience as you can imagine. And it's not just the audience width, but you're not reaching as high quality of an audience also potentially, right? Because your work is not published at a top venue. If it's published at ISCA, Micro, HPC, ASPLOS, those are the top conferences in at least computer architecture, mainstream, right? Of course, some of them are valued more by some people depending on their biases. But again, getting published at top places has a value. Your work becomes more visible, basically. The other thing is inherently, if a work is published at some place, people have this confirmation bias, let me put it that way. They basically trust the work much more. This is a bit unfortunate, unfortunately, this is a bit unfortunate, basically. If you publish a top paper at ISCA, let's say, or even some venue that's peer reviewed, immediately other people trust it, right? Oh, it's published at conference X, conference Y. So immediately you have a trust relationship to that paper until it's broken, of course. Or sometimes, but breaking that trust relationship may be much more difficult for a paper that's published at a top venue, right? So these are the benefits of getting published. So if you have great work, that's why it's important to push your work to be published at a top venue that's very visible, that hopefully everyone reads, right? Because if you don't do that, you would be doing, let's say, a disservice to yourself and your work, because you would be settling for something less in the end. And that less may or may not have as much impact. Now, this doesn't mean that not all works that are published at not so top venues don't have impact. Or sometimes unpublished works also have impact, actually, because someone discovers them. But it's more effort, basically. If your work is published at a top venue, you're more likely to, if it's good, of course, it's more likely to have impact. If a work is published at a lower venue, or if it's not published at all, it's less likely to be trusted and then less likely to have impact. So as a researcher, you would like to actually push forward with these top venues, as you can imagine, right? Again, this is human behavior playing role. Again, you cannot change this behavior. You cannot say to this person who is designing Intel's next generation chips, don't just read papers from ISCA, also read 10 other conferences. Well, they're going to say, go away, I don't have time, right? So you cannot change that behavior. But you could make the best out of your work by pushing your work to the top conferences, of course, right? So that's the idea, basically. Of course, as you publish, so there's also something interesting. Exactly, yes. It'd be easier to convince more people. And also, it'll be easier for other people to see your work. So also, for example, ISCA is interesting because a lot of people think it's the top conference. I believe these 4 conferences are all top conferences. I'm more inclusive. But some other communities, for example, some people in networking, for example, they are more likely to read ISCA papers because they think it's the conference that is the most relevant to them, for example. So that's the idea, basically. It gets more visible. So that said, I think it's important to make your work as visible as possible. But this doesn't mean that some work that's not published, that's published at lower places, don't get visible, especially if you already published a lot of top works at top places. Now you built a lot of credibility and people understand that some works don't get published at top conferences because of their review process. As I said, Ambit was rejected 4 times, right? It got published at Micro. I've had papers that were rejected even more times, and they got published at ISCA. And then maybe we will talk about that actually. Maybe we'll talk about a related work to that. It was actually rejected by lower tier conferences for, again, unfair reasons. Eventually it got published at ISCA. Yeah, it also depends on which reviewers you get, by the way. There's some randomness in the process, clearly, because somebody is going to select reviewers, and if they were not the good reviewers, you may get 5 terrible reviews. Sometimes you get 2 reviews or 3 reviews. Basically you get, sometimes you get randomness in the process. That's unfortunate. That's bad. And there's no way to fix it at this point. I think there are ways to actually, I'm constantly trying to improve the process, working with other people. There are other people who are trying to improve the process. But again, there's so much that can be done to improve it as much as possible. Okay, I think we spent a lot of time, but it's based on your questions. Hopefully this was useful. If you have any more questions, feel free to continue on Piazza. But I think at this point, I'm going to stop. And we will continue the discussions next week. And again, next week may be a recorded seminar. I'm not sure yet. Or maybe we'll continue with another paper. But regardless, please check your email. And the week after that, on the 15th of October, we're going to start with your presentations. Okay, have a good Friday and weekend, and look forward to seeing you next time.